Hey you guys, thanks for watching this video. We're going to be looking at radioactive decay in this example. So the only difference between this one and the previous ones was now the rate is going to be negative because it will be decreasing. Additionally, we won't necessarily be using it like this. We're going to look at this just a little bit differently. The difference is that we're going to look at this in terms of the population, but instead of population, now we're looking more in terms of mass, because we are looking more now at substances or isotopes or elements. All right, like one that we're going to see is carbon-14. None of that really is as important. I'm not so concerned about the scientific facts behind this as I am with the ability to work with this equation right here, which is how this equation is derived. So what I want to do is, instead of looking at this in terms of population, we're going to look at this in terms of weights, which would give me more of a function that looks like this, where the weight is a function of time, where we have the initial weight and e to the power of the rate times t, but instead of the rate as well, we're going to look at this in terms of k, which is kind of a rate, but it's a decay rate or a decay constant, if you will. And the k will be important because we're going to have to figure out what it is in both the problems that we're going to be doing. So here we have the half-life of radium-226 is 1,590 years. If a sample contains 300 milligrams, how many milligrams will remain after 2,000 years? One thing we'll want to identify in this is that 2,000 years is more than the half-life. So in 1,590 years, this 300 milligrams will be cut in half, at least, because, again, we're looking at more years than the 1590. So in this problem, we have an initial weight or mass. Now, please don't get all scientific nerdy on me here, okay? Because yes, milligrams is more of a mass. I'm using weight. Part of that is because we've already used an m of something before in this set of problems. So I'm just going to say it's weight. It's not going to matter. The process is still the same, whether we use weight or mass or population instead of a W, M, or a T. Okay, but in this example, I am going to use W as though it were a weight. Whether it is a weight or a mass, I don't even care. So we have the time, but the first thing we're going to want to do is figure out that K, which we don't have. We have the initial weight and the time, but again, not the growth or the decay rate, the decaying constant. So what I'm going to have to do is figure out what that is, and since we don't know the corresponding ending weight with the initial weight, we need to compare something arbitrarily. So I'm going to choose 1 gram as our initial weight, and I have e to the power of k, which is what we're trying to find, but the time it would take for that 1 gram to be cut in half is that 1590 years. So this is going to be equal to the weight after 1,590 years, which is 1/2. Now to solve this, you can use a natural log or a common log. Most of you in the class prefer that I use a log, and since that's multiplied by 1, by the way, what I can do is get rid of it, or in other words, I made it a phantom 1, and from here what I would do is take the log of both sides. And again, the only reason I'm using a log is because most of the people in the class prefer to use it that way. Now the reason I want to do this is because now I can take this power and move it to the front of this log. So this is what I have now. Log of 1/2 equals k times 1590 times the log of e. And if I wanted to solve for k, what I would do is I would take all of this stuff and divide it by itself. 1590 times the log of e. But if I do it to one side, I must do it to the other side as well. Just like this. And what that does is it gets rid of the 1590 and the log of e. Some of you know that if I use the natural log, it would get rid of that natural log of e because it would just be 1, which we're not so concerned about. Again, the reason I'm doing this is because most people in the class prefer to use logs, and there's nothing wrong with that. You're going to get the same answer either way. So next thing we're going to want to do is just plug this into the calculator. That will give us the decaying rate or the decaying constant. And that gave us a negative 0.000436. And this is a negative again because we have decay instead of growth. The next thing I'm going to want to do in this problem is look at the original function there and figure out what we can replace in order to solve this. And since we have a k, if we look at the time in years, we're looking at 2,000 years from now, where the initial weight of this sample is 300 milligrams. So here's my new function, which I've replaced my initial weight, the k, and the time in years is 2,000. From this point, I can just go ahead and plug this directly into my calculator in order to figure out what the weight will be after 2,000 years. And again, just looking back, we went over this before, but this is more than 1,590 years, so we would expect the weight to be less than 1/2 of that 300. And the answer that I get is 125.43 milligrams of this radium-226. And this will be our final answer right here. Now that was a little bit of a long process simply because we had to find the k, and we have this e to the power of this stuff. That's long because of the extremely long decimal, which some of you guys can store in your calculators and then use that, which may be a little bit easier for you, but it may also give you a little bit different of an answer than this 125.43. For example, during class we got 125.45. Some of you also made the mistake of maybe just typing it in wrong, so you just want to check that k. For example, one student put in 200 instead of 2,000. Another student put in 30 instead of 300. Other people didn't use enough zeros in this decimal, and so it gave them far different answers than what we have here. Alright, thanks for watching this video. Please subscribe to the channel, leave your comments, and share your videos with your friends taking your math classes. Again, thanks for watching.